Maximum walls destroyed by robots, we are given three arrays: robots, distance, and walls. The robots array is going to be the coordinates for every robot on a number line, and same goes for the walls. Distance is basically distance a bullet from a robot that will travel in either left or right direction, right? So basically, if we have a rough diagram, this is the number line, and we have a couple of places where we have robot, right? Couple of places where we have wall, uh, right? And every robot can either uh, emit a bullet in either left direction or right direction, right? Not both. So one of the direction needs to be chosen, and the thing is that bullet will travel distance amount either in left or right, whichever direction it was emitted, and all the walls that are in the range of that distance. Suppose if we have right, if we have this robot and the distance for this robot, uh, first of all, this robot emits a bullet towards the left direction, so the bullet may travel this much, or it may travel this much, right? So in that case, that bullet will destroy this wall, and same goes for the other side. One of the side needs to be chosen, and overall we want to find the unique walls that all the robots together is going to destroy, right? So one wall should not be double counted. And the last thing is, if there is a robot in the path of the bullet that is emitted from another robot, right? For example, if this is the robot R2 and this emits a bullet in the left direction, and it was supposed to travel this much, but it can only travel this much because there is a robot in between. So robot is a blocker, it won't let any bullet pass through, right? So what if there is a wall in the place of that robot? There can be a robot and a wall at the same position, right? In that case, uh, there is specifically mentioned this one statement where a wall and robot may share the same position. The wall can be destroyed by the robot at that position. So I'm assuming that R2 will not be able to uh, destroy this wall. Reason being, it can only traverse, and the moment it reaches this point, the robot is the one that the bullet faces first, than the wall. So the robot is going to stop, and this wall can only be destroyed by this robot, right? So it's ambiguous, it's not very uh, like it's not confirmed, but we are assuming this is going to be the case, right? So how are we going to solve this problem? That's a good question. Let's see. The first thing is, for any robot, if we try to see for every robot how many walls the bullet is going to uh, you know the number of walls that it's going to destroy, then we see that it can choose either direction, right? One of the direction it can choose. So there is a dynamic programming aspect to it, but before that there is something more. What is that something more? Well, for a robot, I would want to know, I can in O of 1 operation tell how much distance the bullet is going to travel either in left or right direction. If the direction is decided based on dynamic programming, suppose it is already decided, and I can always tell in O of 1 operation that this is the distance, how much it is going to travel, right? So if this wall array were to be, sorted in ascending order, in that case, I can easily use binary search to determine the distance, right? Suppose bullet travels in the in the left direction, then using binary search, I can get the start index, and the end index will be the position where the robot is situated, right? That means current position is the end index, right? So in this case, if the walls were sorted, then I can always tell this particular index in log of n operation, which is good enough, at least for now. But this is not it, right? What if I were to choose the right direction? Well, the same goes for that. I can always do a binary search, uh, the end index for the right direction. The next thing is, yeah, dynamic programming will handle the maximum case, right? It will keep track of the maximum case till a certain point. I'm going to choose a bottom up approach, sorry, top down approach, not bottom up, but will just walls being sorted do the job, because we have a blocker as well, right? Robots act as a blocker for the bullet. In that case, for a robot, I would want to know the start index, but that start index will be dependent on the previous robot's position, and same goes for the end index. The end index is going to be dependent on the right or the next robot in line, right? So in line means I can always have robots also in sorted order, so that I can block the start index and the end index based on the distance that I calculate, and the distance or the robot position, previous robot and the next robot position, right? Based on the start index and end index can be blocked to a certain distance, right? And yeah, so if I write the steps, not in complete detail, but in some rough form, sorry, steps. The first thing is sort walls and robots array. Since we have robots and distance, uh, you know, very deeply connected, reason being the indexes are matching here. So I can create an index array and sort it based on robots, so that I don't affect robots and distance connectivity, right? So sort index array based on robots. The next thing is run our dynamic programming. So what are the states that we are going to require for dynamic programming? We have talked a lot about the binary search part of it, but DP is something that's still remaining. Since we don't have a choice in terms of index, right? We have to choose one index and then do the binary stuff part, binary search part of it. But the next state will be the direction, right? That's where we have choice, and the choice is left or right, right? So we can have a previous direction as a state. That means I can write it here. Two states. One state will be the index. There's no choice. Previous direction is the next thing that we want. Values can be 0, 1, right? 0 and 1 can determine left or right. That's it. And based on that, we are going to block or values for start and end index. The third thing is, for every index, determine the start index and end index using start distance using binary search of over walls array, binary search of start distance as a value that we are going to search over walls array, and end distance values over walls array, right? So this is it. These three steps is what we need to do. We need to also keep track of, or at least handle, edge cases where the robots and walls take the same position, right? So yeah, let's do this. So first thing is sort walls array. So we don't have any connectivity with walls array, right? So we can just straight away sort this. The next thing is, so we need to sort index array based on robots array, right? So I'll create an index array which will contain all the indexes till this much size. So let's get the size, robots dot size. This is going to be, initially all values will be default. I'll use the iota function to populate the values which will be the index, right? So this will populate values 0 to n minus 1. The next thing is we can sort this now. Index dot, let me call this indices instead. Indices. So this will be sorted based on the robots array. So let me get the LHS and RHS. This will be a return on robots of LHS less than robots of RHS in ascending order. Now we can create a DP function. I'll create a let's see, let me create a lambda function because we need to pass distance, robots and walls, right? So if I create a function outside, then I would need to write a lot of things. So let's create a lambda function. Let me see, auto instead. This will be a solve function which will capture all the variables outside, robots, distance and walls, and it will also have variables which will be the index and integer previous direction. What did I say? That was previous direction, right? Yeah, previous direction. So we can have these. The next thing, it's going to return an integer, and I hope this is correct in terms of syntax. But yeah, so if index is going to, the base case will be where index is already at nth position. In that case, will return 0. So if index is greater than equal to n, then I can return 0. Otherwise, I will need to play or do all the manipulation and everything based on the indices index, right? So let me get a variable robo index or robot index, which will be index value of the robot which is at the starting position. So this will be the robot index, and next thing is we want the start distance and end distance, right? We need to do the start and end distance. Let me get that. Start distance means the leftmost point that the bullet is going to reach, right? The leftmost point the bullet reaches. There can be couple of cases here. The start distance uh, reaches till case 1 will be start distance reaches till previous robot position plus 1, right? Why did I do plus 1? Because it's not going to affect the wall at the position where the previous robot lies, right? That's why we did plus 1. Next thing is case 2 will be, I guess, the normal distance that we calculate based on the distance array, right? That's going to be till let's say distance array, right? And the robot position, right? Robots of, let me write it in pseudocode fashion, robots position minus the distance, bullet distance, right? Yeah, so this is the thing. Then there is another third case. Why did I say third case? See, let's see. Here we have unique walls, right, that we want to calculate. What if the previous robot fired a bullet in the forward direction towards this robot which we are calculating right now? So it has already traversed or covered some walls, right? So we don't want to double count those walls. So based on the value of the previous direction integer, we can manipulate this case, use this case. So start distance reaches till previous robot's bullet position plus 1, right? So that's going to be previous robot. I'm not going to calculate here, I'll do it in code. Previous robot bullet position plus 1, and that is only if previous direction value is 1. That is, we are assuming 1 means in the forward direction, right? So if previous direction is equal to 1, then so one of the case is going to be the one which is going to win and decide the value of start distance, right? So let's say and by the way, previous direction is equal to 1 will only be true if there is a robot beforehand, right? So and so that we don't overflow. I am not sure if we are going to overflow if we don't have this condition, but still let's be safe, right? So if a previous robot exists, yeah, so first thing first, we are going to get or initialize this as the robot position or the bullet position. So robots of robot index minus distance of robot index, right? So this and this robot index here and here, they're both connected, so it's going to be the same value, right? So this is the first value of start distance handling case 2. What about this one? Previous robot. So here also, if a previous robot exists, let me write it like this. Let's say this is case 1, case 2. If a previous robot exists, right? So I can create a block for handling case 2 and case 3. So if there is a previous robot, how can I decide if there is a previous robot? Well, uh, if index is greater than 0, that means there is a previous robot. And so here I did index, not robot index. Why? Because robot index can be anywhere, I don't know. But index is what is sorted, right? That means I am at the second robot position if index is greater than 0, second or third or fourth, whatever. And there is a previous robot that lies, right? Then, so we can handle case 2 and case 3. So start distance reaches till position previous robot position plus 1, right? That means start distance reaches, but what if the start distance that the bullet would have reached without any other robot existing, right? That means what if this value was already larger, right? So we want the larger value among the two, right? So that we get the right value. So it's going to be start distance, comma, previous robot, so robot index or robots, uh, let's say indices of index minus 1. This is the robot plus 1, right? So this is case 2. Case 3 will be if the previous direction is equal to 1. That means there is a previous robot and that robot fired a bullet in the right direction. That means the start distance will be either these values or the maximum value that this position among the start distance. So whatever the maximum value is among them, that's going to be our answer. So start distance, let me write it first before it gets more confusing. So previous robot bullet position plus 1. That means this is the previous robot. This is the previous robot bullet position. And lastly, I did a plus 1. Why? Because for obvious reasons, so that the wall at the position of the previous robot is not affected, comma, start distance, right? Yeah. So there is one case where things might go wrong, and that case would be where what if this value turns out to be larger than start distance that we have decided, right? Then that is a problem, or is it not? Let's see. What if this value becomes larger than the robot's position itself, right? So start distance means this particular current robot fires a bullet in the left direction, right? That's what we are assuming. But what if start this value becomes larger than the robot's position itself, right? So just to handle that case, I can just copy this value. Let me write it here. Int previous robot bullet position, right? So previous robot bullet position, if this value does not exceed Uh, there are other ways to handle this as well, but let's see. Let's handle this way itself. So previous robot bullet position should be less than uh, you know what, I don't want to complicate things. I would do it this way. So by the end of this, right, uh, so by the end of this, I'll take the start distance and take the minimum value among the start distance and the current robot position, right? Robots of robot index, right? So this way I can always, you know, overcome the edge case. So by now I have the start distance. I can do a binary search for at least one of the choice, and then we can handle the end index, right? So I'll have uh, let's see, I'm going to now search for the start index using binary search, right? That's what we need to do. Find start index using start distance. So I'm going to search this value start distance as a lower bound value over the walls array, walls array, and the start distance, right? So this is going to give me the index instead of the iterator, right? The next thing is we need to be, I guess, careful in the sense that, yeah, I guess we are good. But the problem is, I also want to calculate or take into account those walls which are, uh, yeah, I mean, which are at the position of the robot, right? That means I am going to find the index in the walls array that will be analogous to the robot index, right? So it's going to decide the position. I can always use binary search here. Let me write it and then explain. So uh, let's see, current index, I guess that's going to be the lower bound. Actually, it's not going to be the lower bound value. What if there are multiple walls? There can be multiple walls, or it may not be the case. But let's assume that there are multiple walls. Then in that case, I would want to take into account all the walls, right? That means I don't want the lower bound value. I want the upper bound value of this robot index uh, position, right? So upper bound value was dot begin, comma was dot end, comma robots of index or robot index, right, minus was dot begin. Lastly, this is going to be the case. Let me have an answer is initially 0. Let me call the one choice that we have already. That means current index minus start index plus solve function. This means that this current robot has fired the bullet in the left direction. That means the next value of previous direction will be 0. So index plus 1 comma 0, right? Okay, so now comes the end index, right? So end index is equal, sorry, end distance is what we need to calculate first. End distance is equal to, uh, so I'm not going to write the cases here, right? Or should I write it? Let's see. Let's write it. So the rightmost point the bullet reaches, end distance reaches till the robot position plus bullet distance, right? If there is a previous robot, if there is a previous, so there is no previous robot, right? So this is never going to happen. So we can end this case right now. The only other case that I see is when uh, the end distance reaches the other, yeah, I mean the only other cases we is this one, that is case 2, previous robot, instead of that we have next robot, end distance reaches till next robot position minus 1, right? So whichever is going to be the minimum value, that's what we are going to choose, right? So minimum of uh, robot robot index, uh, robot index plus distance of robot index, right, comma next robot if it exists. So I can do it with a check, right? If index is less than equal to n minus 1 or less than n minus 1, that means I have a robot towards my right, or yeah, towards my right. That means end distance is going to be blocked based on the next robot position. So the minimum value among the two choice is going to be my end distance. That's going to be robots of indices of index plus 1 minus 1. Why did I do minus 1? Because I don't want to interfere with the walls that are at that position. So yeah, so now I can do the end index. That's going to be a upper bound this time, right? Upper bound walls dot begin. Let me copy this. I'm searching the value end distance. So this is going to be this, but the start index, that is the current index, right, in this choice is not going to be the upper bound value but the lower bound value. Why? Because I want to handle in this case also all the walls that are at the position of the current robot position, right? That means I don't want to do upper bound, I want to do lower bound. So here the current index will change based on lower bound, not upper bound. And yeah, I guess we are good. Answer is equal to max of answer comma current index, actually end index, this is going to be a bigger value, minus current index plus solve function call with the index plus 1, and the bullet was fired in the right direction, so 1. And lastly, return answer. I can return uh, the dp function solve comma index plus 1, that's going to be 0. Initially, what should be the previous direction value? Well, if the previous direction value was left, right, which doesn't exist, right, but still if it is 0, that means left direction, then it's not going to affect anything, right? So I can choose 0 as my starting previous direction value, right? So let's see, I'm a little bit reserved in the sense if it's going to work or not. Of course, so solve function, let's see, I think there is, so I am not very familiar with lambda function, but let me see if this will work. uh, int comma int is the value that we return, and these two are the arguments. I don't think we need this. And let's see, okay, yeah, this works. Let's this can be memoized because it will TLE most probably. So let's memoize this with a 2D vector. uh, n plus 1 comma 2, because 0 and 1 are the two values. Negative 1 is what I'm initializing it with. If cache of index of previous direction is not equal to negative 1, then I can return this value. Otherwise, let's see, memo is here, right? Yeah, let's see now. Let's submit this. I think this can still TLE because of the way I'm writing the lambda function. Okay. I think there is a way I can do a auto. By the way, I think this will pass otherwise if we write it in a normal fashion, or if we do it in bottom up, this will work just fine. But let me see if this will work. Uh, so where is the other call? Yeah, I mean self self and solve. Let's see now. Oh, so we need to, yeah, let's see now. Okay. Hmm. I think this will be self also. I don't remember the syntax. Let's see now. Yeah. So let's submit this. I think this will optimize the calls, recursive calls. Yeah, this works. All right. So time complexity will be, let's see, this will be n log n, this will be n log n, this will be extra space, whatever. This is where the core is. So it's going to be what 2n, O of 2n, but inside we have binary search. This will be log n, this will be log n, this will be log n, this will be log n. So it's going to be overall 4 log n, which is log n. So for every recursive call, that's going to be the case. So it's going to be O of 2n log n, which is kind of n log n overall. Yeah. So I think that's the time complexity. Space complexity is going to be O of 2n, I guess, and O of n. So it's O of n overall space complexity. And yeah, that's the problem. Thanks.